Hello and welcome back to another homework video. So to start this video, we're going to be using heat and mass transfer analogy to derive and explain the Lewis relation. So to start, to do this, we have the Sherwood number, which is going to say that the mass transfer coefficient times the length is going to be over the diffusion coefficient. We are also going to be using the Schmidt number, which is going to be the viscosity divided by density times the diffusion coefficient. So in this, for Sherwood, this is going to be SH. Schmidt is going to be SC. So this is in terms of, this is for mass transfer. And for this analogy, we also need to look at heat transfer. And for that, we're going to be using the Nusselt number and the Prandtl number. So for the Nusselt number, that's going to be the heat transfer coefficient times the length over the thermal conductivity. And then Prandtl's number is going to be, let me move this up, is going to be the heat capacity times the viscosity over the thermal conductivity. And then looking at these four equations, we can see that the Sherwood number and the Nusselt number are related. And we can also see that the Schmidt number and Prandtl number are going to be related. And then we can also rewrite this Sherwood number to be equal to some concentration times the Reynolds number to the 1/2 times the Schmidt number to the 1/3. And this was discovered experimentally. But now we also want to take the Sherwood number and divide it by the Nusselt number. So we can do that down here. Sorry, before I do that, I'm also going to rewrite the Nusselt number. Similar to how we did with Sherwood, it's going to be a very similar equation. So it's going to be, the Nusselt number is going to be equal to some concentration times the Reynolds number to the 1/2, but this time it's going to be times the Prandtl number to the 1/3. Okay. So now if we're doing the Sherwood number divided by the Nusselt number, we're going to have the mass transfer coefficient times the length over the diffusion coefficient. And then for Nusselt number, it's going to be the thermal conductivity divided by the heat transfer coefficient over the length. And then this length simplify to be the mass transfer coefficient times thermal conductivity over diffusion coefficient times the heat transfer coefficient. And now looking back at these equations that we wrote, if we divide the Schmidt number by the Nusselt number, these terms cancel and we're left with that there, which is going to be the Schmidt number over the Prandtl number to the 1/3. And then this is going to be equal to the Lewis number, which is going to be the thermal conductivity over density times heat capacity times the mass transfer coefficient, all to the 1/3. Sorry, this is actually the diffusion coefficient. Okay. So this, the Schmidt number over Prandtl number is the Lewis number. And then so is this, this term here is also Lewis. Oops. Okay, so now let's just rewrite this. So we have the mass transfer coefficient times the thermal conductivity over the diffusion coefficient times the heat transfer coefficient is going to be equal to the Lewis number to the 1/3, which is equal to the thermal conductivity over density times heat capacity times diffusion coefficient to the 1/3. Okay, so then if we simplify this, we're going to be left with the thermal conductivity over the heat transfer coefficient times the density times the heat capacity times the Lewis number. It's going to be equal to the Lewis number to the 1/3. Or sorry, this was the mass transfer coefficient. So then this term here, we're going to say that it's about equal to 1. So then if we divide this over, we're going to be given that the mass transfer coefficient over the heat transfer coefficient times density, heat capacity is going to be equal to 1. And then from the beginning of the video, we want to get the relationship in terms of heat capacity. So we have to multiply the heat capacity over, we're going to have that heat capacity is going to be equal to the mass transfer coefficient times density times heat capacity. And then this relationship can be used when we have problems using both heat and mass transfer. So now we're going to kind of switch gears a little bit, and now we're going to derive and show a relationship between the wet bulb temperature and the adiabatic saturation temperature. So to draw this, we're going to have the water here. There's going to be some temperature of water at the interface, and then some temperature of water as it goes to infinity. And then we have the air coming across, and then the air has some temperature also. And then as the air goes across, it's going to supply energy to the water. So we want to look at the heat and mass transfer for this problem. So for heat transfer, it's going to be convective. So we're going to have the heat transfer coefficient times the area times the change in temperature. And because the air is supplying energy, this is going to be the temperature of the water minus the temperature of the air. So this is for heat transfer. It's going to be equal to the mass transfer, or the mass transfer equation, which is going to be the mass transfer coefficient times the area times the change in concentration, which is going to be concentration of water at the interface minus the concentration of water at infinity. And then this is going to be multiplied by lambda, which is going to be enthalpy of vaporization. And then this is just the energy required to get the liquid into a vapor. Okay. So then if we remember the Lewis relation from earlier, we said that the heat transfer coefficient is equal to the mass transfer coefficient times the density times the heat capacity. We can use this to again relate heat transfer to mass transfer, which is what we're trying to do in this problem. So let's plug this equation in for H. So we're going to have the mass transfer coefficient times the density times the heat capacity times the area times the temperature of the water minus the temperature of the air and be equal to the enthalpy of vaporization times the mass transfer coefficient times area times the concentration of water at the interface minus the concentration of water towards infinity. And then we can see that the mass transfer coefficient and the area are going to cancel out. So we can simplify this. That density times heat capacity times the temperature of water minus the temperature of air will be equal to enthalpy of vaporization times the change in concentration of water at the interface minus the concentration of water at infinity. So here's our final equation for how we can solve problems using a heat and mass transfer relationship and solving problems that include both heat and mass transfer. And this is for evaporative cooling. So now if we want to look more at adiabatic saturation temperature, oops. We're going to have a different setup for this. So for this, we're going to have a pipe. And then we're going to have water around the pipe. And then here we have air flowing through. So this is T1 and T2. And then for this, we're just saying it's T1 and T2 because we said it's adiabatic. So the temperature of the water and the temperature of the air are going to be the same. So that's just T1 and T2. This is going to be a very similar setup to before. We're still going to have the heat transfer equation first. We're going to say that the heat transfer coefficient times the area times the change in temperature is going to be equal to, it's still going to be the lambda, which is the enthalpy of vaporization, times the mass transfer coefficient times the area times the concentration of water coming out minus the concentration of water initially. So 1. And then like we said before, we're still going to use the Hw5 relationship, where we said that it was heat transfer coefficient. It's going to be equal to the mass transfer coefficient times the density times the heat capacity. We can plug this in for H like we did earlier. Like we did right up here. So we're still going to have mass transfer coefficient times density times heat capacity times area times the temperature going in minus the temperature coming out is equal to the enthalpy of vaporization times the mass transfer coefficient times area times the change in concentration. And again, we can cancel out these terms. And we're left with the density times the heat capacity times temperature in minus temperature out is equal to the enthalpy of vaporization times the change in concentration. So this is the final equation for an adiabatic saturation temperature example. And if we look back at the first equation that we found earlier, I'll copy it down. I think before I might have had the the T air and TW switched, but that's how it should be, where it's the temperature of the air minus the temperature of the water. So you can see how these are basically the same equation. The only difference is that in the adiabatic saturation temperature example, it's just T1 and T2 because the temperature of the air and the water are the same. And then in the first equation, it's going to be the temperature of the air minus the temperature of the water because it's not an adiabatic saturation temperature. But that's how you can use the Lewis relationship to solve for heat and mass transfer problems.